Welcome to polynomials. What are polynomials? They are based on the word poly, which means many, nomials, which means numbers. So really, we're just dealing with things that have many numbers. We're going to take it from the top. I'm going to try and follow the lecture notes as closely as I can so that you can follow along. We'll start off by taking a look at a polynomial in one variable. Polynomial in one variable, which we'll call x at this point, has the form a sub n x to the n plus a to the n minus 1, x to the n minus 1, and so forth until we get right down a to the sub 1, x to the 1, plus, oops, that's supposed to be an a to the 0. And I just draw all of this out to make a quick note on notation. Whenever you see something like this, you get a letter and then a little other letter or number just below the line, these sub-numbers. This is just an idea or a mathematical notation letting you know that you're working through a series of numbers, starting from your highest number and down to the lowest number. In this particular case, wherever you see an A, this is supposed to represent a coefficient. Now, a coefficient is just a very fancy word that describes the number in front of the letter. The number in front of the letter. So these are all coefficients. If you have a number and it is not in front of the letter, like this one down here, we call those constants. And that's just a number. So that's just the start of a little bit of vocabulary that we're going to be working through. When we go through this, we call the term with the highest power, so in that case, this one here, we call that the leading term. And therefore, the coefficient in front of that is going to be called the leading coefficient. The highest power, whatever that ends up being, is called the degree of the polynomial. In a traditional definition of the polynomial, the powers of the variable are whole numbers, 0 and larger, which means you don't get any fractional exponents and you don't get any negative exponents. And by convention, when we arrange the terms, we arrange them in descending order. So your highest power goes first, and then we go down to the constant. A couple of quick examples just to make clear on what a polynomial is and how the vocabulary all works together. Example, we have 3x to the 4th plus 4x to the 3rd plus 12. The degree of this polynomial is 4, and that's because of this power, which is our highest power. The leading coefficient, or the leading term rather, is going to be 3x to the 4th because it's the one that's highest. So there's our highest term. And then finally, the leading coefficient in this case is going to be 3. Because that's the number out front of our highest power. And then finally our constant term is 12. And there's the anatomy of a polynomial. I will do another quick example where it's not quite in order. If we had something like x cubed minus x to the 7th plus 12x squared, it's important to note this is a polynomial still with degree 7. Our highest power is still 7. And that lets you know that our leading term is the one with the highest power. So this whole thing ends up becoming our leading term. And because of that, we have to recognize that the lead coefficient, color do I want for this? We'll do this. The lead coefficient in this case is going to be -1. There's a negative in front of our x, and there's a little invisible 1 that's implied, so that lead coefficient becomes -1. And our constant term in this case is going to be 0, because there's nothing at the end here. So we say that our constant is 0. And then finally, the last example, just looking at the anatomy of a polynomial, is taking a look at something that is not a polynomial. So if we have x to the 4th minus 1 over x squared, this is not a polynomial. The reason it is not a polynomial is because it doesn't quite meet all of our criteria. I could rewrite this expression as x to the 4th minus x to the -2. So now, because our exponent is less than 0, it no longer hits our criteria for a polynomial. By the same reasoning, or at least similar reasoning, this expression is also not a polynomial, 4 root x plus 1, because we could write this as 4x to the power of 1/2 plus 1. So now we have a fractional exponent instead of a whole number exponent. So again, not a polynomial. So those are our definitions. Moving on to the basics of adding and subtracting polynomials. To add and subtract, we simply add and subtract terms with the same degree. So same degree means that we're looking for exponents with the same powers. The other way that we can take a look at that is we're looking for like terms. Always putting together like terms. So we'll start with our first example. Let's say we've got this long expression, 4x to the power of 4 plus 3x cubed plus 2x minus 1. We're going to add that to 7x to the 5th minus 3x to the 4th. Ooh, it's going to be tight squeezing this one in. Minus 7x squared plus 3x plus, that's a 5. And we'll just close off the bracket like that. Should have left myself a little bit more room. However, we persevere. So what we're looking for in this case is we're trying to put together all of our like terms. So the first thing I'm going to look for, do I have any other x to the 4ths? I do. But as I'm looking for the x to the 4th, I notice my highest power is x to the 5th. There's nothing else which matches with our 7x to the 5th, so it's just going to come along for the ride. Then we put together our x to the 4th powers. So that's going to be 4x to the 4th minus 3x to the 4th. Look for anything that matches with our x cubes, and we do. So I'll get 3x cubed minus 7. Sorry, is that an x cubed or an x squared? That's an x squared, sorry. So we have nothing that matches with our 3x cubed. But we do with our 2, nothing matches with our x squared either, sorry. So we can just bring down the 7x squared. The x's do match, so I get 2x plus 3x. And I'm just going to squeeze this down here. And then we get minus 1 plus 5. Now, you don't always have to do it out like this. I'm doing it out like this so that you can see what we're talking about in terms of like terms. Fourths go with fourths. Thirds go with thirds, and there are no other thirds. Squareds go with squareds. There are no other squareds, and so on. So you just try and match those all together, and then the arithmetic is fairly simple. 7x to the fifth, 4x to the fourth minus 3x to the fourth just leaves us with a single x to the fourth. My 3x to the third just comes for the ride. My negative 7x squared just comes for the ride. 2x plus 3x gets me a 5x. Negative 1 plus 5 gets me a positive 4. Subtraction goes the same way. Does the highest term always go at the first? Sorry, I'm being asked. It doesn't have to. It does make life easier if you can always sort of put your highest term right at the front. Then your eyes, when you're scanning, it makes it easier to spot your terms, but it's not strictly necessary, no. Okay, try and give myself a little bit more room this time. So subtraction works the same way. 6x cubed minus 2x squared plus 8x minus 6. Now here's the one thing that is slightly different when we're doing with subtraction. When you've got this minus out front of the brackets, you have to remember to distribute that minus. And we're going to take that the very first step that we do before we do anything else here. So 6x cubed minus 2x squared plus 8x minus 6 minus 2x cubed minus 5x squared plus 3x minus 9. Now, when I take the brackets away, I don't have a negative out front of my first set of brackets, so nothing changes. However, as I move to my second set of brackets, this negative has to apply. So a negative times a positive is still a negative. But a negative times a negative now becomes a positive. And then a negative times a positive becomes a negative. And a negative times a negative becomes a positive. Having done that, now we can look for our like terms to go together. I've got 6x cubed. I've got negative 2x cubed. So those go together. 6 minus 2 simply leaves me with 4. I look for any x squareds. I got a negative 2x squared. I have a positive 5x squared. Negative 2 plus 5 is plus 3. X squared. 8x minus 3x leaves me with a 5x. Negative 6 plus 9 leaves me with a plus 3. So far, so good. Okay, so that's your adding and subtracting. Fairly straightforward, as long as we keep in mind our like terms, and when you're subtracting, make sure that you distribute that negative and change the signs where appropriate. Then just put them all together, and everything's fine. Moving into multiplication, things get just a little bit more involved. So, we're going to deal with something called the distributive property. The distributive property is something that I sometimes also refer to as the kindergarten rule. If you've got a couple of things in your brackets, like this, and then you have something else that's multiplying them, so I'll throw an X out here. The distributive property says you have to share that in. You can't just multiply the x times the a, you have to multiply the x times the a and the b, which is sort of the same as saying, way back in kindergarten, if you had enough for yourself, you had to have enough for everybody. In a single word, share. So, this is going to multiply by that, and we would end up with something that looks like that, ax plus bx. This rule continues to apply no matter how many things we have in each bracket. So if I had a plus b in one bracket, and then I had c plus d plus e in the next bracket, I have to share everything. That means this a will multiply by c and by d and by e, but then the b is going to multiply by the c and the d and the e. So in the end, when I do all of this, I should end up with 6 terms. Okay? 2 terms by 3 terms gets us 6 terms. So you have a fairly good idea, even before you actually start doing the work, how many terms you should end up with when you do your multiplication. If I had 2 and 2, it would be 4 terms. If I had 4 and 4, it would be like 16 terms. So the number of terms in each bracket, you multiply that, and that lets you know how many there are supposed to be. Let's do a concrete example so that we can actually put some numbers to this. So I will take the very first example that I'm using in the notes. When we multiply 2x cubed plus 3x to the 7th times 5x squared plus 6x plus 1, 2 terms here, 3 terms here, this line should end up with 6 terms. So I will give myself enough space. We start off by going 2x cubed times 5x squared, which gets me 10x to the 5th. And again, 2x cubed times 6x gets me 12x to the 4th. And 2x cubed times 1 just gets me 2x cubed. Moving on to the next term, 3x to the 7th times 5x squared should give me 15x to the 9th. 3x to the 7th times 6x should give me 18x to the 8th. And then 3x to the 7th times 1 gives me 3x to the 7th. And I do have 1, 2, 3, 4, 5, 6 terms. I look then to see if there's anything that's in common anywhere. I have no powers in common. And then by convention, I can rewrite this in descending powers. So 15x to the 9th, 18x to the 8th, 3x to the 7th, 10x to the 5th, 12x to the 4th, 2x cubed. So that should be fairly straightforward. Let me do one other example just to make sure that everything is making sense to everybody. I'm going to skip one example because it's fairly well laid out there, but I'm going to do this example. So I'm going to go on to the example that starts with 4x squared minus 7x minus 3, 2x squared minus 5. The reason I'm choosing this one is because I want everybody to make sure that they pay attention to the positives and negatives. This is most often where you can end up losing marks on a test, or more importantly, where the question ends up going sideways on you, is just not following your positive and negative rules. So 2x squared times 4x squared gives us a simple 8x squared, or 8x to the 4th rather. But 4x squared times negative 5 negative 20x squared. Negative 7x times positive 2x squared gives us a negative 14x cubed. Negative 7x times negative 5 for a positive 35x. And then finally, negative 3 times positive 2x squared is negative 6x squared. Negative 3 times negative 5, positive 15. 3 times 2 should give me 6. 1, 2, 3, 4, 5, 6. Everything's good. And then we put together like terms if we have any. I have no other x to the fourths. I have just the one term of x to the third. I have a negative 20x squared and a negative 6x squared for a total of negative 26x squared. Just the one x term and just the one constant. Just a point of clarity, I've been using the word terms. Each one of those things, anything that's being all multiplied together is a term. And when we're looking at terms, we always try to bring the sign along with it. So this term is negative 14x cubed. This term is negative 20x squared. And then we have a positive 35x. You can include the plus sign in that if you so desire. But always make sure that when you're talking about terms that they include a sign. While we're talking about terms, really quickly, sometimes instead of calling something a polynomial, somebody will be referring to it fairly specifically. Let me check where I've got space here. I'll clear this out for some space. If you've got just one term, that's called a monomial. With an R. A binomial, one can expect, will have two terms. A trinomial, of course, will have three terms. And then beyond that, we don't tend to name them. They just all generically become polynomials. When we're dealing with polynomials, one of the things that comes up fairly often is when you're multiplying two binomials, so two two-term expressions. And when we do that, we use a method called FOIL. So when we're multiplying binomials, we use this term called FOIL. This is going to seem a little weird, but I'm going to do this all out in colors for a second. It takes a little longer, but it's a little easier to see what's happening when I do it this way. So FOIL stands for firsts, outsides, insides, and lasts. And what all of this means is just a way to keep track of how you're multiplying things out. So I will do a generic example first so that you can see what's going on. If I had some expression, x plus y times a plus b, my firsts are the parts that are in the first part of the bracket. So my first letter in the bracket is x, my first letter in the bracket is a, those are my firsts. My outsides are referring to those terms that are right on the outside of the bracket, so my x and my b. The insides are the ones that are on the inside of these pair of brackets, so in this case that will be my y and my a. And then the lasts are referring to the last terms in each bracket, the y and the b. And that's just a way of keeping track of what multiplies by what and in what order. So this would end up being xa plus xb plus ya plus yb. Let's do this with some concretes. Sorry, just before I go on to some concretes, do keep some careful notes on this. Right now what we're doing is we're moving forward, where we're taking two binomials and we're going to put them together and get a single polynomial out of the whole thing, just an expression out of that. A little bit later, I'm going to be talking about how we go from that finished product back to a pair of binomials, which is a process called factoring. So do pay attention to how we get to our solution, because we're going to have to go backwards eventually. Okay, so let's start with this first example. We have 3x minus 2 times 7x minus 2. Our firsts multiply together, and we end up with 21x squared. Our outsides multiply together, and I end up with negative 6x. Our insides multiply together, we end up with negative 14x. And then our lasts multiply together, and we end up with plus 4. Those came together here. Those come together here. These come together here. And finally, these come together here. And part of the reason why we do it in this order is because very often, particularly when you're dealing with the same variables in both sets of brackets, your like terms end up grouped together for you right in the middle, making it really easy to spot what you put together. So our final answer in this case is going to be 21x squared minus 20x plus 4. Everybody still with me on this? Most people seem to be yes. Great. Just waiting for a couple more responses, then we'll keep going. Okay. Still missing a couple of responses, but for the most part, people seem to be with me, so we will carry on. I'm going to need a little bit more room, so I'm going to erase all of this, but the same process still occurs. Now, sometimes you get a string of these things. So in this case, we're going to go with 3x minus 2 times 2x plus 1 times 4x minus 3. Now, nothing's actually changed, but we're not going to try and multiply, then multiply, then multiply. I'm just going to deal with the first pair of brackets, and this third bracket is just going to come along for the ride for a moment. So when I do this, 3x times 2x gets me 6x squared. 3x times 1 gets me the 3x. Negative 2 times 2x for negative 4x. Negative 2 times 1 for negative 2. 4x minus 3 just comes for the ride. As happened before, our like terms are nicely grouped together for us in the middle. Positive 3x minus 4x gives us negative 1x. And now we go through this process again. We can't quite call it FOIL, but we can sort of do that same process. The first times each of those terms, the second one times each in the second bracket, my third one times each in the second bracket. So 6x squared times 4x gets me 24x cubed. 6x squared minus 3 for negative 18x squared. Negative x times 4x gets me negative 4x squared. Negative x times negative 3 for a positive 3x. Negative 2 times 4x gets me negative 8x. Negative 2 times negative 3 gets me a positive 6. So again, it's nicely grouped. Those are like terms there, and those are like terms there, so we can put those together quite nicely. 24x cubed, negative 18, and negative 4 gets me to negative 22x squared. Positive 3x minus 8x gets me negative 5x, and then our constant finishes off the whole thing. Okay, there are a number of special products that are useful to take note of. And I have a whole list of them there in the notes on page 5 under the heading Special Factors, and I'm just going to share the screen on that right now. We'll just do a quick review. This comes in particularly useful when we get to the point where we're factoring, where we're going backwards from our final answer, which looks something like that, and we're trying to find out where it comes from. But what this is basically saying is, if you have some binomial squared, what that's telling you to do is multiply that whole bracket by itself. So you're getting it twice. And when you do that, a nice constant pattern emerges. A squared is your first term, so whatever your first term here is, you're just going to get that squared. Whatever your last term is, you're going to get that squared at the end. And the middle is just your first term times your second term twice. And I'll give you a numerical example of that in a moment so that you can see why it's nice to be able to spot it. The same thing works in the negative version. As long as both signs are negative, you'll do the same thing, but instead of having a positive sign here now, you'll have a negative sign. And then the third option, what happens when the signs are different? Well, then you just have the square of the first minus the square of the second. And those middle terms disappear. And again, I'll show you a quick example of why that happens. If you find something where you have a squared plus b squared, as you're going to discover, with that positive in between, as you're going to discover, this cannot be factored with real numbers. So we're not going to be able to pull that one apart. And finally, the sum and difference of cubes. When we're trying to pull these things apart, they also come apart in a very specific pattern. It's not worth trying to memorize this pattern. Do keep this in your reference sheets, your cheat sheets, in case you're being asked to factor these a cubes, these cubics, because trying to memorize this pattern doesn't work quite so easily. Where does the 2a go in number 1 and number 2? Which are you talking about in terms of the 2a? That? Oh, sorry, the 2ab. It comes from, so I'm going to flip back to to the board, and I'm going to show you how this multiplies out so we can see some of these in action. Oh, that's the wrong camera. Okay, so if you're given a question like this, AB all squared, that squared means you're multiplying something by itself. So that becomes A plus B times A plus B. And here's what ends up happening. A times A, that's no problem. That gets us our A squared. A times B gets me an AB. B times A also gets me an AB. And then the B times B gets me my B squared. And now these come together, and I have two ABs. And that's going to be the pattern each and every time. So I'm going to leave that on there, and I'm going to do one like this with numbers so that you can see how it shows up. I'll do this in a different color, though. So if we had something fairly straightforward, let's just go with x plus 2 all squared. This becomes x plus 2 times x plus 2. Now we follow through. X times x gets me my x squared. X times 2, of course, is 2x. 2 times x is also 2x, and 2 times 2 gets me 4. Putting together my like terms, and I end up with x squared plus 4x plus 4. So you can see what ends up happening. I take my first term and it's squared. I take my last term and it's squared. And then my middle is the two terms together times 2. The same thing happens with the negative version of this. I'm not going to go through that. I am going to show you, though, a difference of squares so that you can see how those middle terms disappear. So our difference of squares is what happens when we have the same numbers in both brackets, but different signs. And what we're going to end up with is something that looks like that. So if I had, let's go with x plus 5 times x minus 5, x times x is x squared. X times negative 5 is negative 5x. 5 times x is positive 5x. And 5 times 5 gets me my negative 25. And as you can see, I end up with positive and negative versions of the same thing in the middle. And they just cancel each other out. And I'm left with x squared minus 25. So the net result is, whatever you've got, square the first term, square the last term, stick a minus in the middle, and you're done. Okay, so let's take a look at a couple of the worked examples, just to make sure that I'm not missing anything along the way. How are we doing on time? 45 minutes in. We are being told to expand on 4x minus 2 all squared. Well, what that means is we start off by taking our 4x minus 2 and multiplying it by 4x minus 2. 4x times 4x for 16x squared. 4x times negative 2 gets me negative 8x. And again, negative 8x. and then negative 2 times negative 2 for a positive 4. Like terms are in the middle, and I end up with 16x squared minus 16x plus 4. Moving on to the next worked example. This one is 3x minus 4, 3x plus 4. So I take a look at that and I notice we are dealing with a difference of squares, same numbers, different signs. So if I wanted to, I could simply jump to the answer, where I square the first term, so 3x squared becomes 9x squared. Square the last term, 4 times 4 gets me 16, and stick a minus in between. If you're not comfortable doing that yet, we can go ahead and work it out the long way. So we still end up with 9x squared is our first term. 3x times 4 gets me 12x. Negative 4 times 3x gets me negative 12x. And then negative 4 times 4 gets me negative 16. These terms cancel each other out, and we end up with that as our answer. Why doesn't the negative 8 and the negative 8 make a positive? Because they're not multiplying. What we end up with is negative 8 minus 8. So one way you can think of that is you owe $8. Now you owe another $8. How much do you owe? You owe $16. Does that make sense? Yes, I was just noticing that same thing, Lauren, that in that worked example, the exponents haven't shown up properly. I need to make that correction moving forward. Thank you. Okay, so this concept that we're dealing with here in terms of the difference of squares also helps us out when we're trying to rationalize the denominator with our radicals. So when we're trying to get rid of that radical sign in our denominator, sometimes we end up with more than one thing in the denominator, and we want to try and simplify that as quickly and as easily as possible. So let's say we have this. I've got root 6 over root 12 minus 3. Now the difficulty here is in order to get rid of this root 12, I can't just multiply this whole thing by root 12 over root 12, because then I'll end up with a root 12 on this 3, and I've still got the same problem. It hasn't actually disappeared. So in order to make this disappear, what I'm going to do is multiply by the conjugate, which is to say the opposite signs. I'm going to multiply this by root 12 plus 3, top and bottom. So as we had a minus 3 there, I'm going to put a plus 3 there. And when we do that, now on the bottom what we have is a very lovely difference of squares. Put these in brackets just for clarity. So now when we do this on the bottom, well, root 12 times root 12 is simply 12. Our middle terms are going to cancel out, as we've seen from the difference of squares, and then our last term, 3 times 3, is 9. So now I have 12 minus 9 on the bottom, and I'll clean that up in just a second. On the top, we still do our distributive property. We still do the sharing thing. Root 6 times root 12, 6 times 12, 74, so we end up with the square root of 74. Root 6 times 3 is just 3 root 6. Now we want to clean this up. So what can we pull out of 74? I'm going to do a quick factor tree on this. 74, is that right? 72, that's better. Divide that by 2, and I end up with 36. Oh, and there it is right there. Back to perfect square. So 72 can be factored into 6 root 2 plus 3 root 6, and then 12 minus 9 gets me a 3. And then the important thing to note at this point, I can take a 3 out of 6, I can take a 3 out of 3, so this 3 will reduce both of those things, top and bottom. That'll go, that becomes a 2, that becomes a 1. And my final answer is 2 root 2 plus root 6. I've done that out in a fair amount more detail in the notes if you're trying to wonder how I'm jumping from step to step, so it should be there for you. Why do I multiply by the negative 3 and not the positive 3? Sorry, in this first line, do you mean?
Sorry, I meant multiply by positive 3 and not, like, why do you have to multiply by the opposite one?
Sorry, where do you see me multiplying? Oh, here.
In the first, yeah.
So we're always multiplying because what we're trying to create is a difference of squares. So whatever this ended up being, so if this was, so let me do another example so you can see what I'm talking about. I'm going to do something similar to this, but slightly different numbers. So if we had 5 over 6 plus root 6 plus 2, and again we're trying to rationalize the denominator, because this is a plus, I'm going to multiply by root 6 minus 2 top and bottom. And when I do that, I create that difference of squares pattern so that this bottom part is just going to come out as square of the first term, 6, and square of the last term, 4. Because maybe I should do this out so we can see it. Root 6 times root 6 will of course get me root 6 squared. Root 6 times negative 2 will get me negative 2 root 6, and then positive 2 root 6, and then negative 4. And we do it this way so that these two terms cancel out and we don't have any radicals left. So the whole idea is to make sure that those radicals are all gone in the end. So this ends up being 6 minus 4, or simply 2. Does that help? Is that clear? Cool. Okay, now we're on to the part that's probably going to take a little bit. We're on to a thing called polynomial long division. Polynomial long division works exactly the same way old-fashioned long division does, which is to say there's a lot of moving parts and you have to keep track of things. I'm going to do a quick review of actual long division just so that people can see it again for those of you who haven't seen it done out in a while. If I'm given something like 1, 6, 2, 6, 4 as an example, and I'm being asked to divide that by 8. If we had to do this by hand and we weren't allowed to use a calculator, we would do something that looks like this, which is literally trying to say how many times can I put 8 into 16264. And what we end up doing is we end up breaking down the number, and we ask ourselves, well, how many times could I put 8 into 1? Well, I can't put 8 into 1. So I move on to the next digit, and I decide I'm going to try and put it into the first 2 digits. So how many times can I put 8 into 16? I can put it in twice. 2 times 8 is 16. I subtract, and there's a 0. I bring down the next number. And then I start asking, how many times can I put 8 into 2? And in this case, the answer is 0. Because I can't do anything with it, I'll bring down the next number just to keep going. How many times can I put 8 into 26? 3 times, because 3 times 8 is 24. I subtract, and I'm left with a 2. I bring down the next digit, and it's a 24. How many times does 8 go into 24? 3 times again. 3 times 8 is 24. I have no numbers left. I have no remainders, so my answer ends up being 2033. So that's just a quick review on how long division works. We're going to use that exact same process, but now we're going to be using polynomials. So, I'm going to try this in blue. If we're given, am I still on the screen? I am. 3x cubed minus 12x squared minus 42 divided by x minus 3. The same way in our regular long division, we say what goes into what. We're going to do the same thing here. So I'm going to end up with x minus 3 being put into x cubed minus 12x squared minus 42. And I've left a blank here on purpose because the first step when we're dealing with polynomial long division is to make sure that we have representation for every power from our highest power down to our constant. So in this case, I have an x cubed, that's fine, and I have an x squared, that's fine, but I have no just x's. So when we're doing long division, we have to state that expressly. So I have to state, do this in a color that's going to show up. I have to state expressly that I have no x's. So I'm going to go plus 0x. And it'll become clear why we need to have that placeholder in there as we go along. So x cubed, I'm going to start by looking at this x, and I'm going to ask myself, well, how many times can x go into x cubed? The other way I can ask that question is, what do I need to multiply x by to make it look like an x cubed? And in this case, the answer happens to be x squared. X squared times x gets me x cubed. However, I don't just have the x that I'm trying to put in, I also have this negative 3. So I have to take this x squared that I put up here and also multiply it by the negative 3, which leaves me with 3x squared. And now I'm subtracting that from this whole thing. So x cubed minus x cubed is 0. That's the way we designed it. That's good. That's what should happen. Pay very close attention to your signs here. I have negative 12x squared minus negative 3x squared, which is basically the same as saying negative 12x squared plus 3x squared. So I end up at negative 9x squared. We bring down our next term. In this case, it is going to be plus 0x, and I start the process all over again. What can I multiply x by to make it look like negative 9x squared? The answer is negative 9x. So negative 9x times x gets me my negative 9x squared. Negative 9x times negative 3 gets me positive 27x. So this is why we needed that placeholder, because we need something that's going to subtract our 27x. Negative 9x squared minus negative 9x squared goes to 0, which it's supposed to do. 0x minus 27x gets us minus 27x. And we bring down our last term. One more time, what do I multiply x by to turn it into a negative 27x? I multiply it by negative 27. That gets me negative 27x here. Negative 27 times negative 3 gets me positive 71. 71? 81. That's better. And then we subtract. The negative 27x minus negative 27x goes to 0. That's the way we want it. Negative 42 minus 81 gets me down to negative 123. Now we do have a remainder, and when we're doing polynomial long division, we have a special way of writing our remainder. We're going to add negative 123 over our divisor, x minus 3. And that ends up being our answer. X squared minus 9x minus 27 plus negative 123 over x minus 3. Okay, so I've got a question here. Can we go back to subtracting the negative 12 and the negative 3? Wouldn't it be negative 15? So this is where we need to be very careful about the signs, and it is where things most often start to go very badly wrong, because if you get the wrong number here, everything else is going to cascade. If we take a look at this, and it's not written out like this, but I write it out, I'll do a quick sidebar here, just in a line the way we're used to seeing it, this would read as negative 12x squared minus negative 3x squared. So we'd end up with a negative beside a negative. And when we do that, negative times a negative is, of course, a positive, which is then going to get us the negative 9x squared. Does that make sense? And that's a very, very common thing that can go wrong when we're doing the polynomial long division. So you need to watch. And that's why I keep writing this minus. If you see a minus and a minus, remember that it's going to go to a plus. Sorry, where are you, Lauren? Three times 12. Oh, where did the 27 come from? 9 times 3 in this step right here. So we've done this, we came down to 9x, and so what did we need to multiply x by to turn it into a 9x squared? We had to multiply it by 9x. The 27 then comes from taking our negative 9x squared and multiplying it by negative 3, which is where our negative 27 comes from. Or a positive 27x rather comes from. So it's that negative 9x times negative 3 to the positive 27x. Okay. Would you guys like to see another one of these done out? Okay, I'm getting an overwhelming response of yes very, very quickly. So I will do out another one of these. These are challenging. And if it wasn't for the fact that they actually do come up in higher level math where you do have to use this skill, I wouldn't try and spend as much time on it. But as you are using this as a prerequisite for future math courses, you are going to need to be able to do this. So let's do another one. Do I have another one prepared? Okay, so then let's try this. If we have 14 x to the fourth plus 12x cubed, and I'm just going to throw in no x squareds just to keep that going. 36x minus 100. And we're going to find out what happens if we try to put that in for x plus 5. Same process right from the beginning. We're trying to get to 14x to the fourth. So x needs to multiply by 14x to the third. 14x to the third times x gets me 14x to the fourth. 14x to the third times 5 gets me 70x cubed. We subtract. That goes to 0. 12 minus 70 gets me negative 58x cubed. And I bring down the 0x squared. How do I get to negative 58x cubed from an x? I'm going to multiply this by negative 58x squared. So negative 58x squared, that should be a 5, not a 6. That should be an 8, not a blob. Negative 58 times 5 gets me negative 174x squared. And again, we're subtracting. So that goes to 0 because we've designed it that way. Watch the negative subtracting. Here, this takes us up to positive 174x squared. How do I turn an x into 174x squared? I multiply it by 174x. Oh, sorry, and don't forget to bring down your next term. So 174x times x gets us to 174x squared. 174x times 5 gets us a relatively large number. 1 second, I'm not doing that one in my head. 870. $36x minus 870x gets us negative 834x. And then the last term comes down minus 100. So we will multiply x by negative 834. Gets us our negative 834x. Negative 834 times 5 gets us the ridiculously big number, in this case, of 4,170. We will subtract. That goes to 0 because we've designed it. Negative minus a negative, and we end up with negative 400. Positive 4,070. That gets written over our divisor. And that's the answer. Yes, that should be a cube. Sorry. You're absolutely right. I just wrote it wrong. I did the right math. I wrote it wrong. So do take note. You can run out of space working on these fairly quickly, so leave yourself a lot of paper when you're working these out, and just go very slowly, making sure that you're checking your positives and your negatives as you go. Okay, I've got about 45 minutes left, a little under, and I still have a bunch of pages to go. Are there any questions on this at this point before I start moving on? Okay. So we carry on. We're going to start now into some factoring. Factoring is related to what we've just done here in terms of this polynomial long division. We're trying to figure out how things break apart. How do we get back to the pieces that make up our question? First thing we try and do when we factor is we try and take a look. Wow, I'm having some difficulty with my pens here. We try and see if there's a special factor that can help us out first. If you recognize that your polynomial has a form that a special product has, you can just go ahead and do that. So, for example, if we had 25x squared minus 16, I immediately note that this is a difference of squares. And how do I notice that that's a difference of squares? Because I have a perfect square at the front. Both 25 and x squared are perfect squares. I have a perfect square at the back. 16 is a perfect square. Separated by a minus, it hits all the criteria for a difference of squares. So I can then note that 25x squared comes from 5x all squared, and 16 comes from 4 all squared. And now I found out what my square roots are. So then I just need to put it into the form that we're looking for a difference of squares. If, however, you come across something that is not necessarily a difference of squares, there are two, or not necessarily different squares, and doesn't necessarily show up on any of your special products lists. There's two possibilities that will be happening. One of them is that the number in front of our first term, in front of x squared, is 1. And the other possibility is that it's not 1. It's something either greater or less than 1. Or higher than 1 or less than negative 1. So we're going to start off with this idea that a is equal to 1. So our general form for this is we're looking at things of the form ax squared plus bx plus c. A, b, and c are actual numbers, and in this case, a is always going to be 1. So let me give you a concrete example of this form. So if we have something that looks like this, I have x squared plus 7x plus 12. The number in front of our x squared is 1. That's fine. And then our other numbers are 7 and 12. What I'm trying to do is I'm trying to play a game here where I want to find out what two numbers multiply to make 12, but add to make 7. Okay? So this is what I tend to do. I take my 12 and I'm going to do find all of the pairs of numbers that multiply to make 12. 1 times 12 makes 12. 2 times 6 makes 12. And 3 times 4 make 12. Well, 1 and 12 either get me 13 or 11. Neither of those is 7, so I don't want that one. 2 and 6 adds to 8, subtracts to 4. Again, not 7. 3 plus 4, oh, those add to make 7? So that's the numbers I want. Because of that 7 there. So, because of that, I can immediately just break this apart into this form, back into the pair of binomials. I can just jump straight to that answer. I'm going to do another one, this time that involves negatives, but it's going to be the exact same pattern. So if I'm given x squared minus 2x minus 15, I'm trying to figure out what multiplies to make negative 15. My answers are 1 and 15 or 3 and 5. Now, because this is negative, one of these needs to be negative. And when I do that, well, it's not going to be those. I can't get to negative 2 that way. But if I have a positive 3 and a negative 5, I can get to negative 2. So those are the terms that I need, and I can go ahead and set it up again. And I end up with an x plus 3 and an x minus 5. And we're done. Now, there's another possibility that comes up, and in fact tends to come up a little bit more often. What happens if a is not equal to 1? What if there is some number in front of x? Well, then we have something slightly more involved. So now we have a not equal to 1. Let's say we've got this one. 6x squared plus x minus 12. Now we're going to do a process that's called AC factoring, and I'm going to multiply my first and my last terms together. So I need to multiply 6 times negative 12, and I end up with negative 72. Now what I'm looking for are the numbers that multiply to make 72 that add to make 1, because there is a little invisible 1 in front of this middle x. So what are all my possibilities for 72? 1 times 72, 2 times 36, let's see, 3 times 24, 4 times 18, nothing by 5, 6 times 12, and 8 times 9. Going through all of these possibilities, looking for what adds together to make 1. In order to get to a positive 1, I would like a negative 8 and a positive 9. And none of these possibilities will get us there. I now take these and I'm going to turn my positive 1x into how I got there. So the 6x squared, I end up with minus 8x plus 9x minus 12. So this 1x comes from negative 8x plus 9x. It doesn't matter in the end what order you put those middle terms into, you'll still end up in the same place in the end. So here's what we do from here. I'm now going to start doing something called factoring by grouping. I'm going to take these first two terms and I'm going to say, what's in common? What can I pull out of both 6x squared and negative 8x? And what I can pull out of both of those is a negative 2x. So there's my negative 2x. And when I do that, I'm left with 3x plus 4. So you can see if I multiplied these back in, negative 2x times 3x gets me back to 6x squared. Sorry, that should be a negative. Negative 2x times 4 gets me negative 8x. So I get back to where we started. I'm going to do the same thing with these two terms. What can I pull out of both 9x and 12? I can pull out a negative 3, which leaves me with negative 3x plus 4. Negative 3 times negative 3x gets me positive 9x. Negative 3 times positive 4 gets me negative 12. And if I've done this stage right, what we can see is that the brackets are exactly the same. Because those brackets are the same, I can actually factor those out as if they were a common term. And I will just stick those out front, negative 3x plus 4. And then my other terms go in the other bracket, negative 2x minus 3. And then we're done. And yes, I was just noticing that I did something slightly different here than I did in the handout. I was just about to mention that. Thank you, Lauren. What I did here that was slightly different is I pulled out the negatives with this. If I had not pulled out the negatives, and it ends up being the same thing because this whole thing is just multiplied by negative 1, I'll go back a step. If I didn't pull out negative 2x, if I just pulled out a positive 2x, then this would have stayed as 3x minus 4. The same thing here. If I just pulled out a positive 3, then that would have ended up as 3x minus 4. That's our common term. And our other bracket would stay positive. I'm going to do one more of these. So now we have 6x squared plus 19x plus 15. Again, I'll take my first term and my last term, and I need to go 6 times 15. Sorry, I'm off the board there. 6 times 15, which gets me 90. My possible factors of 90 are 1 and 90, 2 and 45, 3 and 30, 4 does not go in, 5, and 18. 6 doesn't go in nicely. 7, 8, and then we get down to 9 and 10, which is the pair that I want anyway, because 9 times 10 is the same as saying 9, or in this case 9 plus 10 gets me the 19 that I'm looking for. So then I separate these out, and I end up with 6x squared plus 9x plus 10x plus 15. What can I pull out of both 6x squared and 9x? I can pull out a 3x, leaving me with x plus 3. Nope, that's not right. 2x plus 3, that's better. 3x times 2x gets me 6x squared. 3x times 3 gets me back to 9x. What can I pull out of both 10x and 15? I can pull out a 5, which leaves me with 2x plus 3. 5 times 2x gets me back to 10x. 5 times 3 gets me back to 15. My brackets are the same, so we've done this right. I end up with 2x plus 3. And then my other two terms are in the second set of brackets. Any questions on those? These are the sorts of things I think I've provided you with a sufficient amount of practice in the homework. However, if you get to the end of the homework and you're still like, I still don't feel comfortable factoring, go ahead and send me an email. I have more examples for people to work through. I have pages and pages and pages of factoring practice that I can send to people if need be. No, we'll always leave our final answer like that, because if we multiply them, we just end up right back where we started. Okay, moving on to rational expressions. So, rational expressions is a wonderful place where absolutely everything that we've learned so far all comes together in one question. Our fraction rules are going to apply, our factoring rules are going to apply, our distributive rules are going to apply, being able to cancel up and down and crosswise on fractions is going to apply. It's all coming together. So here we go. I'm going to start off straight off with an example. There are no new rules to introduce when we're doing rational expressions. It's all just the rules we already have, just applying them. So we're given an example. 1 over x squared minus 9 plus 3 over x squared plus 5x plus 6. At its root, this is basically just a question of fractions. I want to put these two fractions together, which means I need a common denominator. In order to find a common denominator, I need to figure out what's missing from both sides so that I can multiply them and make a common denominator. When we're faced with polynomial expressions in our denominators, our instinct should be, first and foremost, to factor them. Let's see how these pieces are working together. So when I factor this, it's going to come out like this. I have a difference of squares here in this first one. So this becomes x plus 3, x minus 3. When I factor this, I want those numbers that multiply to make 6, but add to make 5. In this case, those numbers are 2 and 3, so I end up with x plus 2 and x plus 3. And when we do that, we should notice that in each fraction, I already have an x plus 3 in the denominator, which means that all I need to do on this fraction over here, our right-hand fraction, is I need to multiply it by the term it doesn't have. it doesn't have x minus 3. So I'm going to multiply this side by x minus 3, top and bottom. The same thing happens going the other way also. If I look again, x plus 3 is in common. This has an x plus 2. This side does not, so it's going to multiply by x plus 2, top and bottom. And as soon as I do that, I get my x plus 3, x minus 3, x plus 2. X plus 3, x minus 3, x plus 2. Now I have a common denominator. As soon as you notice that you have that common denominator, just write it out once and leave it in factored form. We don't need to multiply it all back together. On top, we do need to do the multiplication. 1 times x is x. 1 times 2 is 2. 3 times x is 3x. 3 times negative 3 is negative 9. Then we put together all of our terms that are all of our like terms on top. So in this case, I'll have x plus 3x to get me 4x. 2 and negative 9 gets me negative 7. Our denominator just comes for the ride. And that is the final answer in this case. Okay, now it can get a little bit more complicated. Sometimes you'll find that there's an on top you'll have something that cancels with something on the bottom. Go ahead and make that simplification if it happens. Let's take a look at an example though. Instead of adding and subtracting, if we're multiplying or dividing, and I'm going to do a division question. Oh, can we cross out the x minus 3, the x plus 3? No, because they're multiplying at this point. Because they're multiplying, they don't actually cancel each other out. Okay, any other questions before I move on? Sorry. Okie doke. Okay, so now we're being given something that's a little bit more involved. I've got x squared minus 9. Am I still on the screen here? There we go. X squared minus 9 over x squared plus 6x plus 5. This is going to be divided by x squared plus 8x plus 15 all over x squared minus 1. Lots of polynomials, still just fractions, one fraction dividing another fraction. The first thing that I'm going to do is I'm going to start factoring this first fraction. So x squared minus 9 is the difference of squares. X plus 3, x minus 3 on top. On the bottom, what multiplies to make 5 but adds to make 6? 5 and 1 multiply to make 5 and add to make 6. So I end up with x plus 1 and x plus 5. Now it is still a fraction question, and when we're asked to divide fractions, what that actually means is we're going to flip it over and multiply it. So now my bottom from the first line becomes the top in my second line. It's still a difference of squares. I can make this x plus 1, x minus 1. What multiplies to make 15 but adds to make 8? We end up with x plus 3, x plus 5. Now comes the fun part. After you've gone through all of the work, now I've done it very quickly. I don't expect you guys to be able to do it quite that quickly yet. But once you've done all the work to get all of this stuff factored, then we can start to look for the places where we can just start to get rid of numbers and make our lives easier. First thing I check is top and bottom. I don't have anything going straight up and down that cancels very nicely. However, I do have an x plus 1 here and an x plus 1 there, and those can just easily disappear. And then I've got an x plus 3 here and an x plus 3 up there, so those can disappear. And then I've got x plus 5s on the bottom, x minus 3 and x minus 1 on top. And for the purposes of this, we can just go ahead and say, well, x minus 3 times x minus 1 is just going to be x minus 3, x minus 1 on top. And then I'm going to get x plus 5 times x plus 5 on the bottom. And that is a perfectly correct answer. If you get that far on a test and that's what you give me, I am happy. If you feel compelled to go one step farther, you can go ahead and multiply out your numerator. And you can recognize that your denominator can be compacted down to just look like that. This is correct. This is correct. It's whichever one makes you more happy. Okay, I have managed to whip through this slightly faster than I expected. I still have 13 minutes to spare here. So as I moved fairly quickly through this, I do have the time to answer questions on any part of this lecture that I've skipped through so far. Which are they looking for in the upper level courses? It's going to depend on the context. So you want to be able to do both, because sometimes you're going to want to see things in factored form simply because you're trying to work with the individual pieces and what they might mean in a graph. Sometimes you just want it nice and compact because you're actually at the end of everything and there's nothing more to do with the question. So if you can be comfortable doing both, you'll be the most happy. Any other questions at this point? Okay. Let me then pull just a couple of quick questions from the homework, just to do a couple of examples. Just before I do that, because I'm sure people will start to file out shortly, another quick poll. Did this lecture change your life? Lovely. Thank you all very much. Okay. So I'm being asked, just before I try doing a polynomials question, I'm being asked about trig homework, question 5F. Let me pull up question 5F. Determine the quadrant and reference angle for the following. Okay, yes, I think I was about to do this one the other day, and then I left it as an exercise for you guys, so now I will do this one out. So what we're looking for here is 9 pi over 10. I'm throwing these on really quickly. 3 pi over 2, pi over 2. 9 pi over 10, if we ignore the pi part for a second, we look at that, it's 9 over 10. It's just a little less than 1. Okay, and there's 1 pi. So immediately we know, I'm going to be somewhere in here. I'm going to be somewhere in the second quadrant. Then from there, we're trying to find the reference angle, so we're looking for how close it is to that x-axis. And there's a couple of ways that we can do this. One of the ways that we can figure it out is we can try and do this. If we want to stay in radians, I can do pi minus 9 pi over 10. Fractions are fractions, so we need to have a common denominator. That becomes 10 pi over 10 minus 9 pi over 10, so we're left with 1 pi over 10. 1 pi over 10, remembering that pi is equal to 180 degrees. So this essentially says I have 180 divided by 10, so that's going to be 18 degrees. So my reference angle here is either going to be 1 pi over 10 or 18 degrees. Why is it pi? Because my closest x-axis is at pi. If I had an angle here, let's call that sorry, just trying to come up with one in my head very quickly. Let's say we had something randomly like 7 pi over 4. I want to know now the difference to this x angle. I would do 2 pi minus 7 pi over 4. Why not 9 pi over 10 minus pi? Because then I would end up with a negative in my angle, and I want a positive angle. So I always subtract the larger number first and then the smaller number. Yes. Does that clear that up then? Cool. Okay, I was pulling up some of the polynomials homework. Let's take a look at yes, if you feel comfortable with this work, feel free to leave. I'm just doing some examples for the next couple of minutes. So if you're good with everything, you don't have to stick around at this point. But we'll go from there. What about exponents? In what context? You want some examples from exponents? Okay, let me see if I can have some of the exponent stuff. Is there a particular question you'd like me to go over? Question 1H. Okay, so question 1H. 1 over 3 to the negative 1 minus 2 squared over 5. Okay, so this is from the exponents homework. This is question 1H. Okay, so we start on the first fraction here. 3 to the negative 1. That negative 1 says we should be on the other side of the fraction line, so that just becomes a 3. 2 squared is 4, and nothing's happened with the 5. Still just a fractions question at the end of the day, so we need to make common denominators as long as we're subtracting. So we treat the 3 as 3 over 1, and I multiply it by 5, top and bottom. And then I end up with 15 over 5 minus 4 over 5, which should just leave us at 11 over 5. Question 2C says, uh, 8x squared y to the negative 2 z to the negative 5 all over 2x to the negative 2 z to the 4. The whole thing is raised to the power of negative 2. So whenever we're dealing with these large questions like this, my inclination is always to simplify inside the brackets before trying to apply that external exponent. First thing I can simplify, 2 goes into 8, and that becomes a 4. The next thing I can simplify are the exponents. I have x squared on top. I have x to the negative 2 on the bottom. When we're dividing exponents, we subtract. But we're going to be subtracting a negative. So that's 2 minus negative 2, and that makes that go away. There's nothing that matches with the y, but I can do the same thing there. With the z, I have a 4 on the bottom. We subtract those, and it goes like that. So when I clean that up now, I'm going to end up with 4 x to the power of 4. Y is still to the negative 2, and z is now to the negative 9. And this is all raised to the power of negative 2. At this point, I can go ahead and share that exponent, and it's going to go on to all 4 terms in here. Going in slow detail, this then ends up as 4 to the negative 2. This ends up as x to the negative 8, y to the positive 4, and z to the positive 18. Cleaning up the negative exponents, my y to the 4th stays on top, my z to the 18 stays on top. 4 to the power of negative 2 becomes 16 on the bottom, that's 4 squared, and the negative puts it to the bottom of the fraction. X to the negative 8 becomes x just to the 8 on the bottom of the fraction. Uh, 1I. Oh, okay, yes, we can do 1I fairly quickly. I'm going to leave this up for people still marking that one down. 1I reads as 3 over 5 all to the negative 2 times 2 over 3 all to the negative 1. The negatives tell us that we're going to flip the fractions in both cases, and then I'll also apply the exponent. So I flip that over, and I end up with 5 squared over 3 squared times 3 over 2. I can do 5 squared and 3 squared, and I end up with 25 over 9 times 3 over 2. Before I multiply, I recognize that I can reduce this way, and that 9 goes down to a 3. So now I have 25 by itself on top, and 3 times 2 gives us 6 as a denominator. And then I will do 2f fairly quickly, and then that'll be our time for today. 2f fortunately does go relatively quickly. X squared y over xy squared plus xy over x squared y squared. Again, still a fraction thing, so we're trying to make common denominators. The only difference between these denominators is this is an x squared versus just an x. So in order to make these denominators match, all I really need to do is multiply this side by x over x. And then I have a nice common denominator of x squared, y squared. On top, x times x squared gets me x cubed, y. Nothing has changed on this side, so I just leave it as xy. And because I can't put together the tops, I just leave my answer in that form. What did I say? Yes, x times x squared, x cubed. Yes. Okay. Did that bottom right y should be to the power of 3? Nope. Is that what the original question says? Sorry, did I write down the question wrong? Oh, sorry, yes, those should be cubed, both of them. Can't read my own notes. Okay. That's our time for today. I hope I didn't confuse anybody too badly with that last question. If you've got more questions, please bring them to class on Thursday. If you're planning on writing a test, why is the answer different on the homework? Maybe that's one of the ones that I have taken note of. Yes, that answer in the notes is wrong. Oh, no, I see what's happened there. Have I lost everybody already? Sorry, so what's happened here? I've seen what's happened. This can reduce. I have x's and y's everywhere. Because of that, I can reduce some of these x's and y's. I can take out 1y from both sides, so that takes that down to a 2, and those disappear. I can take one x out of here, which takes an x off of there, and an x off of there. So I end up with x squared plus 1 over xy. My apologies. I think it's getting late in the day. Okay, I really do have to leave it at that at this point. I think I'm doing more harm than good if I carry on at this moment. Thank you, everybody, for today. Bring your questions to class on Thursday. If you know that you're planning on writing a test and you can let me know in advance, that would be great. If you're not planning on writing a test and you just have questions, feel free just to show up for the questions. If you're not planning on writing a test and you don't have any questions, I don't need to see you. As for the rest of you, I look forward to seeing you all on Thursday. Have a very good evening.